The requirements for grounding equipment conductors, or GECs, to cold water pipes vary by local authority having jurisdiction, or OJ. Some AHA may require GEC to be connected to cold water pipes, while others may not. There are several reasons why an AHA might require a GEC to a cold water pipe. Firstly, cold water pipes are typically metallic and provide a low resistance path to ground. By connecting GEC to cold water pipes, it helps to ensure that a fault current can be safely dissipated into the earth. There are also reasons for not requiring a GEC to a cold water pipe. Firstly, modern electrical systems often have multiple paths to ground, making it unnecessary to connect GEC to cold water pipes. Secondly, in some areas, cold water pipes may be made of non-metallic materials, which would not provide a suitable grounding path. Thirdly, some AHA may consider it unnecessary to connect GEC to cold water pipes if there is a separate grounding electrode system installed. The National Electrical Code, or NEC, does not explicitly require GEC to be connected to cold water pipes. However, it does state that all electrical systems must be properly grounded. It is generally considered best practice to connect GEC to cold water pipes, where possible. However, if the AHA does not require it, and there are other suitable grounding paths available, it may not be necessary. Whether or not it is acceptable to not bring a GEC to a cold water pipe depends on the requirements of the local AHA. It is important to consult the local electrical code and obtain clarification from the AHA to ensure compliance with local regulations. Grounding is a critical aspect of electrical safety. It provides a low impedance path for fault currents to return to the source, which helps to trip circuit breakers or fuses and to energize a faulty circuit. This protects people from electric shock and prevents damage to equipment. The grounding electrode system is the primary means of grounding an electrical system. It typically consists of a ground rod, a ground ring, or a metal underground water pipe. The grounding electrode system must be connected to the equipment grounding conductors and the neutral conductor of the electrical system. The equipment grounding conductors provide a path for fault currents to return to the source from electrical equipment. They are typically connected to the metal enclosures of equipment, such as appliances, motors, and lighting fixtures. The neutral conductor provides a return path for current in a normal electrical circuit. It is typically connected to the grounding electrode system at the service entrance. There are several types of grounding electrodes that are permitted by the NEC. These include ground rods, ground rings, metal underground water pipes, and concrete encased electrodes, also known as UV ground. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Ground rings are made of bare copper wire that is buried in a circle around a building. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements. Concrete encased electrodes are made of bare copper wire that is encased in concrete. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be connected to the grounding electrode system and the neutral conductor of the electrical system. The connection must be made in a manner that ensures a permanent and reliable connection. The equipment grounding conductors must be sized according to the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of the equipment grounding conductor based on the size of the overcurrent protection device. The equipment grounding conductors must be connected to the metal enclosures of equipment, such as appliances, motors, and lighting fixtures. The connections must be made in a manner that ensures a permanent and reliable connection. Grounding is a critical aspect of electrical safety. It is important to ensure that all electrical systems are properly grounded in accordance with the NEC and local electrical codes. Improper grounding can lead to electric shock, fire, and damage to equipment. When dealing with electrical systems, safety should always be the top priority. Always de-energize circuits before working on them and use appropriate personal protective equipment such as gloves and safety glasses. If you are not comfortable working on electrical systems, it is best to hire a qualified electrician. The AHJ plays a crucial role in ensuring electrical safety. They are responsible for enforcing the NEC and local electrical codes. They also inspect electrical installations to ensure that they are properly grounded and that they meet all applicable safety requirements. If you have any questions about grounding requirements, it is best to contact your local AHJ. They can provide you with specific guidance on the requirements in your area. In addition to the NEC and local electrical codes, there are other resources available that can provide information on grounding. These resources include the Institute of Electrical and Electronics Engineers, or IE, and the National Fire Protection Association, or NFPA. These organizations publish standards and guidelines on grounding that can be helpful in understanding the requirements for grounding electrical systems. Grounding is a complex topic, but it is essential for electrical safety. By understanding the basic principles of grounding and following the requirements of the NEC and local electrical codes, you can help to ensure that electrical systems are properly grounded and that people are protected from electric shock and other electrical hazards. The purpose of grounding is to provide a low impedance path for fault currents to return to the source. This helps to trip circuit breakers or fuses and to energize a faulty circuit. Without proper grounding, fault currents can flow through unintended paths, such as through a person's body, which can cause electric shock. Grounding also helps to reduce electrical noise and interference, which can improve the performance of electronic equipment. The grounding electrode system is the foundation of the grounding system. It provides a connection to the earth, which helps to dissipate fault currents. The grounding electrode system must be installed in accordance with the NEC and local electrical codes. The equipment grounding conductors provide a path for fault currents to return to the source from electrical equipment. They are typically connected to the metal enclosures of equipment, such as appliances, motors, and lighting fixtures. The equipment grounding conductors must be sized according to the overcurrent protection device protecting the circuit. The neutral conductor provides a return path for current in a normal electrical circuit. It is typically connected to the grounding electrode system at the service entrance. The neutral conductor must be sized according to the NEC and local electrical codes. Ground fault circuit interrupters, or GFCIs, are devices that protect people from electric shock. They work by monitoring the current flowing in a circuit and comparing it to the current returning. If there is a difference in current, it indicates that a fault current is flowing to ground. The GFCI will then trip the circuit, interrupting the flow of current and preventing electric shock. Arc fault circuit interrupters, or SIs, are devices that protect against fires caused by arcing faults. Arcing faults are caused by damaged or deteriorated wiring. The SI will detect the arcing fault and trip the circuit, preventing a fire. Surge protective devices, or SPDs, are devices that protect against voltage surges. Voltage surges are caused by lightning strikes, power outages, and other events. The SPD will divert the voltage surge to ground, protecting electrical equipment from damage. Bonding is the process of connecting all metal parts of an electrical system together to create a low impedance path for fault currents to return to the source. Bonding helps to reduce the risk of electric shock and fire. The NEC requires that all metal parts of an electrical system be bonded together, including metal conduits, metal enclosures, and metal water pipes. Static electricity is a buildup of electrical charge on a surface. Static electricity can cause sparks, which can ignite flammable materials. Static electricity can also damage electronic equipment. There are several ways to reduce the risk of static electricity, including using anti-static mats, wearing anti-static clothing, and humidifying the air. Lightning protection systems are designed to protect buildings from lightning strikes. A lightning protection system typically consists of air terminals, conductors, and a grounding system. The air terminals are installed on the roof of the building and are designed to intercept lightning strikes. The conductors carry the lightning current to the grounding system. The grounding system dissipates the lightning current into the earth. Electrical inspections are conducted to ensure that electrical systems are installed in accordance with the NEC and local electrical codes. Electrical inspectors will check for proper grounding, proper wiring, and other safety issues. If an electrical inspection fails, the homeowner or building owner will be required to correct the deficiencies before the electrical system can be used. Electrical safety is a serious matter. It is important to take precautions to protect yourself and your family from electric shock, fire, and other electrical hazards. If you are not comfortable working on electrical systems, it is best to hire a qualified electrician. When working on electrical systems, always to energize the circuit before starting work. Use appropriate personal protective equipment, such as gloves and safety glasses. Never work on electrical systems in wet conditions. If you see any signs of electrical damage, such as frayed wires or cracked insulation, have the problem repaired immediately. Never overload electrical circuits. Use extension cords sparingly and never run them under rugs or furniture. Keep electrical appliances away from water. If an electrical appliance falls into water, do not touch it. Unplug the appliance immediately. Teach children about electrical safety. Explain the dangers of electricity and how to avoid electric shock. By following these safety tips, you can help to protect yourself and your family from electrical hazards. The NEC provides comprehensive guidelines for grounding and bonding electrical systems to ensure safety and minimize the risk of electrical shock, fire, and equipment damage. Understanding and adhering to these requirements is crucial for electrical professionals and anyone working with electrical installations. Here are some key aspects of grounding and bonding as outlined in the NEC. Firstly, grounding electrode system. The system connects the electrical system to the earth, providing a path for fault currents to flow back to the source. Common grounding electrodes include metal underground water pipes, ground rods, ground rings, and concrete encased electrodes, also known as UFA grounds. The NEC specifies the requirements for the size and installation of these electrodes. Secondly, grounding electrode conductor. This conductor connects the grounding electrode to the electrical system's grounded conductor, typically the neutral conductor, at the service equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Thirdly, equipment grounding conductors, or EGC. These conductors provide a low impedance path for fault currents to return to the source from electrical equipment. EGC are typically metal conduits, metal raceways, or green insulated wires that run with the circuit conductors. The size of the EGC is determined by the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. Fourthly, bonding. This involves connecting all metal parts of the electrical system together to create a low impedance path for fault currents. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. The NEC requires bonding of metal enclosures, metal raceways, metal water pipes, and other metal parts that are likely to become energized. Fifthly, ground fault circuit interrupters, or GFCIs. These devices are designed to protect people from electric shock by monitoring the current flowing in a circuit. If a ground fault is detected, the GFCI will quickly trip the circuit, interrupting the flow of current. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Sixthly, arc fault circuit interrupters, or SIs. These devices are designed to protect against fires caused by arcing faults. SIs detect the unique characteristics of arcing faults and trip the circuit, preventing a fire. SIs are required in many areas of the home, including bedrooms, living rooms, and dining rooms. Seventhly, surge protective devices, or SPD. These devices are designed to protect electrical equipment from voltage surges caused by lightning strikes, power outages, and other events. SPD divert the surge current to ground, protecting sensitive electronic equipment from damage. The NEC recommends the use of SPD in all electrical systems. Eighthly, isolated ground receptacles. These receptacles are used to reduce electrical noise and interference in sensitive electronic equipment. Isolated ground receptacles have a separate grounding conductor that is isolated from the building's normal grounding system. Ninthly, data communication grounding. This involves grounding the data communication cables and equipment to minimize electrical noise and interference. The NEC provides specific requirements for grounding data communication systems. Tenthly, healthcare facility grounding. Healthcare facilities have unique grounding requirements to protect patients and staff from electrical shock. The NEC provides detailed requirements for grounding electrical systems in healthcare facilities. Understanding the NEC requirements for grounding and bonding is essential for ensuring electrical safety. By following these requirements, electrical professionals can help to protect people from electric shock, fire, and equipment damage. Always consult the latest edition of the NEC and local electrical codes for specific requirements in your area.